In listen-only mode.
Welcome everybody. One second, make sure we're recording for our posterity. Talking, audio. Okay. Are we recording? Okay. All right. Welcome everybody to the Sustainable Energy, Sustainable Home Seminar Series, sponsored by the USB and Building Council, Green Remodeling, and a host of local and statewide businesses. We'll talk about our sponsors in just a second, but thank you all for coming. This is an 8-part seminar series. We kind of do a comprehensive overview of residential sustainability, starting from the economic side, where does it make sense to invest your dollars, moving through the building systems, HVAC, insulation and wall systems, and how you build a tight and proper home, and then into renewables, which are kind of the final phase of a sustainable home, which is once you've got a nice energy efficient home, how do you make your energy carbon neutral, essentially, or with renewable resources. So tonight, our topic is passive house, and we're talking about incredibly tight and energy efficient homes and the design that makes that possible. And we've got Skylar Swindon and Scott Weidlar from here. They're passive experts that are here to tell you how you create a tight and energy efficient home. A couple of housekeeping items here. We're really busy tonight, which is great. We're going to ask that any spillover attendees kind of fill in the side here so we're not in the way of the camera and recording this for posterity. As far as the space, we are hosted in this classroom by the Integrated Design Lab, which is from the University of Idaho. They've got some expensive equipment on that side, so for our bathroom breaks and such, we'll go out this door, the long hallway, all the way around. There's some bathrooms down that way. We'll do that about an hour into the seminar. If you're not a sponsor of the series, it's $10 to attend. That covers our snacks and beverages, and that's accepted over there in a cash box. If you make checks, it's payable to USGBC Idaho, and go ahead and make sure that happens before you leave tonight. Evaluation points in front of you, and that's to make sure we make the class good for all of you. So please provide your feedback. Let us know what you want to hear, and we'll try to accommodate that. Can you advance the slide? Fine print, hard to read. I am going to go ahead and call them all out. Air conditioning. We've got Avant properties, 3 better homes and gardens, 42 degrees north. We've got the Boise Weekly, which helps put the word out and their print advertising. Building energy, which is energy rater and verifier. So once a building is completed, they go in and make sure that it's performing to the specs that it was designed to. Earthcraft and sustainable homes. Franklin Construction, building statewide organization. They've got stores throughout Idaho selling building products. Flying Cowboys Design Build is a local design and build company. Gravitas Design is a design company designing nice homes. Do one more, please. Green Remodeling has for this series since the beginning. Josh Vogel is the owner, and he's been a content provider. He's been he's been up front here telling people about the information they need to know about sustainable energy, sustainable home for 8 years. Idaho Power, we all know them. They're a local utility provider. They've made possible this webinar format so we can put this out statewide. Johnson Brothers Windows and I believe they call doors as well. Osprey Building Performance is another building energy rater verifier. Renewable Energy Solutions company works with renewable energy. Renewable energy on your home, they'll help you out. solar cascade, they're in the solar photovoltaic. And USB building helper item with cascade SS. I believe that's all the housekeeping items. This is an interactive seminar, so please ask questions of our presenters, and they'll be happy to answer. And then at 8, we'll take a break, about 10 minutes, bathroom break. There's snacks in the back. We've got beverages and snacks, tea, soda and beer, and a little bit of wine. And then we'll start back up, and we'll finish up at 9 o'clock. So I'm going to hand it over to Skylar and Scott, and we'll get started. Thanks for coming. Thanks, Chris. Scott. Thanks everyone for showing up here. Is my mic good? Scott and I are going to be doing a little passive house primer. Like Chris said, feel free to ask any questions. Stop the presentation. We've got to skip some slides to answer questions. We're happy to do that. So feel free to interrupt. That's okay with Scott.
So yeah, just a little bit about my partners here tonight, and we're a new design building company in town. We do design, passive house consulting, and demo contracting.
I work for a firm that's based out of McCall called Steel, and our focus is high performance insulation, barrier systems, as well as moisture management and waterproofing systems. A good portion of the services that we do is a lot of forensic consulting work on projects that are built generally in the McCall area that are experiencing the extreme climate up there, whether it's ice damming, heat loss, or comfort issues. So in addition to that work, we also do the passive consulting, several different types of energy analysis, and also on-site testing and verification. For the last 3 or 4 years, I've actually been working for a firm called Hammer and Hand out of the Portland and Seattle area, where I've worked on about a dozen or so certified passive house projects and several net zero and positive energy projects as well. So a lot of the information that I'm sharing today is coming from that experience and working with that type of buildings. No presentation on green building or low energy building would be complete without kind of a look at the big picture. So this graph here is taken from Architecture 2030, and it's just that kind of outlines the magnitude of energy consumption by buildings in the United States. You can see that compared to industry and transportation, when you look at overall U.S. Energy consumption, it's really dominated by building operations, which is energy use and energy consumption in buildings. And then a good little slice of that is building construction and materials. And I just want to kind of zero in on the building construction materials side of things. I think Josh Bogle touched on this in his presentation last seminar, I think in December. Is this like a lot of preservationists and historical folks beat the drum about how historic preservation is important because building energy, the energy that goes into building the building is far more important than the energy used over the life of the building. But the reality is energy consumption is really piece of the pie in terms of the energy use of the building. And by embodied energy, the actual materials that go into building that building are dwarfed by the operational energy. And that's not a hit against historical buildings. I think I'm a huge advocate of historical preservation and historical buildings, but I think folks in that world need to get their facts straight in terms of, you shouldn't do it for the embodied energy aspect of it. Here's another graph that essentially shows the embodied energy, which is the energy that it took to build the building, versus the energy use over the lifespan of the building. And this one plots out to 90 years. You see when we're dealing with low efficiency buildings, the operational energy rapidly dwarfs the embodied energy. As you get more efficient, the time span increases. You get the ultra low energy buildings like a passive house that's using a fraction of the energy, and where you really even should start the debate or the discussion about embodied energy. And then it's also good to keep in mind, in terms of embodied energy, one of the biggest factors in the building really is the foundation system and the steel components and the concrete components. The biggest chunk. And so in that first pie graph that I showed was looking at energy use across
not just electricity, but all energy. And this really just shows the impact building operations have on electricity consumption, where building operations take about 75% of all our electricity used in the United States. Graph here is another 2030 graph, basically showing historical and projected energy growth in the transportation sector, the industry sector. This goes all the way out to 2030. And this graph right here, this blue chart here, is what's projected if we continue on as business as usual, building out to 2030, where our building emissions continue to grow. And the goal with 2030 and passive house and REACH codes is to push direction and actually have buildings start to be part of the solution. And this is another tenet of the 2030 challenge, is that we have a huge opportunity ahead of us with by 2035, about 75% of all buildings will either be new. Go ahead.
Can you give a little more background on the 2030 challenge?
Yeah, I mean, it's essentially started by Ed Mazaria. You want to give a little? Yeah, and it's essentially a lot of it's kind of like there was a really big push, especially during the recession, to get a lot of initiatives passed to put people back to work, retrofitting and improving buildings and making building codes more stringent. And the goal is that by 2030 we can have our buildings can be carbon neutral, essentially. And so, and Ed was one of the really early passive solar guys, and so a lot of the things that we're talking about today are things that he's been a proponent of for 20 to 30 years or longer.
Oh, at all? He said the volume is horrible here and all. We've had some issues where
I'll hold it right here. How's that? This is another 2030 graph, which basically shows carbon emissions from the building sector projected out into 2050. And if we continue on with business as usual in terms of our building codes and our building energy use, even if we add 100 nuclear power plants to offset the additional emissions from our buildings, we'd still have increased emissions. And in comparison, if we ratcheted up our building codes and adopted things like passive house in our retrofit buildings and in new construction, we actually have the opportunity to make a huge impact versus adding additional production. So that's just kind of the contrast of the power of conservation over additional power generation. The folks in here are probably pretty savvy, but just a reminder in terms of energy consumption or electricity consumption in the state, a lot of people have the misconception that it's clean and it's hydroelectricity. We shouldn't really worry about it. But in reality, the U.S. grid is broken up into three sections. We basically have the Western Interconnect, the Eastern Interconnect, and then the Texas Interconnect. And so essentially all the electricity in the Western grid pretty much flows freely between the whole region. And so any hydroelectricity that's produced in Idaho can get shipped anywhere. And so if we can conserve a kilowatt of hydroelectricity here, then that prevents a kilowatt of coal being burnt somewhere else. This shows the true, when you look at the grid as a whole for the Western Interconnect, this is kind of our breakdown here in terms of energy, electricity production, where it's really focused, the dominant source of our electricity is from coal and natural gas. 68% of our electricity produced in the West comes from fossil fuels and nuclear. Then Scott, give a little bit of background on the passive house standard now.
Information about why this is important, and so what we're really good to learn about that, the passive house standard, what that is and what it's changed about. And but I put a slide in here about a little bit about the history in North America, and there is actually a history of super insulation, building buildings with a lot of insulation, and also the idea of a kind of a passive solar house with a lot of glass using the sun to heat the house. And these are several examples. On the left there's a house in Saskatchewan, I think in 1977. And William Shercliffe, he has a lot of books about super insulated houses. These are just several examples that back in the 1970s and 80s, there was a lot going on in North America that was sort of leading up to the passive house idea.
It's good to point out on that on this first project here, this like a lot of these houses are still lived in today. And when you go back and look at some of these early passive solar homes or these super insulated homes, the projects, the things that are still working on these projects are the things like the windows and the airtight shell and super insulation. But for the most part, the solar thermal systems have been stripped off of the building due to maintenance issues, and the PV systems are gone. And so you'll see a lot of our emphasis in our presentation is about the passive parts that actually don't move and that are with the building for the life of it.
So then, in the kind of the late 80s in Europe, the development kind of took off from the North American side. They got the ideas, and there were several businesses. There's in the middle there you can see this is sorry about that. Go through all these. There we go. So these two gentlemen, this is a Swedish physicist, Professor O. Adamson, and then this is Dr. Wolfgang Feist. And they were sort of the founders of what's the modern passive house standard. So that was done in Germany. And Dr. Feist is still sort of leading the charge in the international arena of passive house. So the standard was developed in Germany, and we're going to go through kind of all the principles, but it is a German-based standard with sort of a history that came out of North America. So, you have anything to add on that? So here are a couple of sort of the first projects. This one on the left is the first true passive house that's sort of using all the tenants that we have today. And that was designed by Dr. Feist and his team in Darmstadt, Germany. Then this is 1991. So there have been, basically from 1991 until 2003, there has been a lot of development in Europe. They've done a lot of work, a lot of monitoring, testing. This has been entering the marketplace in Germany. And so finally, basically a student, and she's now the founder of the Passive House Institute US, Katrine Klingenberg, was the first to implement the passive house. That's not actually true, it is the biohouse that was.
Yeah, but she was really the one that brought it across the pond for sure.
So she kind of imported it from Germany, and this is that first project.
So yeah, she was a German student that was doing an exchange program, an architecture program at Ball State, and she was kind of amazed by how different the architecture programs are in Germany compared to the U.S., and it really has a core focus in building physics and the science side of things in Europe. And then she came to the U.S. and was surprised how it was really kind of more focused on art studio and kind of the feelings of the architecture. And so she felt like there was a lot to bring to the table in the U.S. for sure.
As an example of what you can do that can still be a passive house. So these are extremely energy efficient buildings. Just to show a little bit on the architecture side that they can do nice works of architecture. This one is in Switzerland. It's a multi-family, it's just a small 3-unit house. This is a house in New York. A couple of projects that we looked at associated with. One on the left is in Salt Lake City and designed by Dave Brock, and I actually was working with him and worked a lot on that project. And the one on the right is a very nice project in Oregon that Skylar was involved in.
Yeah, so that's a net zero energy project. It's, in addition to being passive house certified, it also has a Swiss certification called Minergie. It is a LEED Platinum building. And it was a really cool project to work on for sure.
And then the passive house, I personally feel it's really important to say that it's not just for single family houses. So when we talk about passive house, it can really be passive building. And so here's a couple of examples of larger scale multifamily projects. Skylar has helped on that one on the left. This is a big, huge development in Innsbruck, Austria that's to the passive house standard. And it's not even necessarily stopped, it doesn't stop at residential. So there can be commercial buildings.
Grocery, supermarkets, sky rises. pretty much just, we're going to get into the details of it, but it's really just an energy budget that any building can work towards.
So what is it? What is it? So we were the principles and sort of the science of what makes it, but these the sort of ideas I think are really what you come away with. If you have someone interested in the idea, I think that these principles of air quality, so superior comfort, and I think that comes out. Obviously, there's a lot of insulation in this house. There aren't any cold spots. There aren't any drafts. You're in front of a window. You don't feel that cool air on the window. They're very, very good. The envelope is very, very tight. And the air quality is very good. The air tightness is kind of a core tenet of the passive house standard. And with that, you have controlled ventilation, so you have a continuous flow of fresh air at all times. Another benefit is that the envelopes are extremely durable. So they're through the air tightness, through the use of insulation, these envelopes will last. And, this is a project in Switzerland. They don't build things to last, 20, 30 years. They're expecting it to last 100 years. And another idea is the idea of resilience, that if there were a utility outage, power outage, or something like that, that these projects can actually kind of hold their heat in for, a couple of days. It's not going to go instantly down to too cold.
Yeah, that's just another view of that Karuna project, and like the slide says, it's a lot of folks in the passive house industry really use passive house as the gas pedal for achieving a net zero site energy project. This project, which is the Karuna house that we showed earlier, you can see the sign of the part of the PV array here, but this is a 4,000 square foot house, and it's able to achieve net zero with the 10 kW array in Portland region, which we get less PV output than we would here in Boise. And if we had just designed this project to the LEED standard, for example, and just had done the LEED Platinum, our array would have probably been 3 times the size. And so we were able to by investing less in the renewables, we're able to put that into the shell and get really high performance windows. These walls are R60 walls, R100 roof assemblies, R40 plus foundation systems.
Okay, so now we can really dive into the principles of what makes a passive house a passive house. And this isn't really breaking news. All of this stuff. People do bits and pieces of this, I think, and in Boise, people are doing a lot of these things already. But it's really bringing all these things together and in the proper way that makes this possible. So we start with this little kind of model house. The obvious thing is the insulation. So a continuous layer of insulation, and it can be called super insulation, but it's just a good amount of insulation. It doesn't have to be extreme necessarily. Thermal bridge free, so that's the second tenet of the standard, and that means that you can't have a steel beam protruding through from the inside to the outside. And you can't have on a foundation that's letting heat go right in. So it needs to be, it's basically keeping your continuous insulation.
Think thermos bottle.
Airtight envelope. Exactly what it says. These are very they don't have many leaks at all. So we'll talk a little bit more about that in a little bit. High performance windows and doors. So if you want to be able to see out of your house, you have to have, something that allows you to maintain the heat. So good windows, normally triple pane windows, especially in colder climates like here.
And insulated frames, yep.
Yeah. Then you want to cover these last couple?
Yeah, and then there's the balanced heat recovery ventilation. We're making the building tight. We're able to control the airflow through it. A really high performance, 90% plus efficient ERV or HRV that's able to bring fresh air into the house and remove pollutants. And then a big key here is sometimes passive house and passive solar kind of get confused. And although in our energy calculations, we do part of the energy calculations and a lot of energy optimization is taking into account solar gains. But these projects aren't the mass and glass, old school passive solar projects where we try to capture as much solar energy as possible and then try to in a slab or in water bottles or in rocks. It's really about optimizing the shading strategies and having these really, really high down so we don't have to rely on huge diurnal swings of bringing in temp energy and then trying to store it overnight where the house just loses all that energy. It's really about moderating the heat levels and the temperature in the home.
So you mentioned the ERB and the HRB.
Yeah.
So what are those and what's the difference?
I'll get into more depth in that, but basically they're a box.
The question was, what is the ERB or the HRB and what's the difference?
Yeah, essentially they both recover heat energy. So if you have air exhausting out of the building, your stale air in your home, you're exhausting that out and you're bringing fresh air in, and that air coming in is getting tempered by the air leaving through a core in the building. And so it's basically this box with two really efficient fans that provide you constant air exchange without a huge energy penalty. And the difference between the heat recovery and the energy recovery ventilator is the energy recovery ventilator not only recovers the heat, but it also recovers moisture from the airstream. And I'm going to go into more detail on that in a little bit.
Another question?
Yeah. Comes to far, there's Germany and Canada that gives us still about 80 days of far. So here's what we can do in the flash out the far.
Excuse me, what was it? Yeah. So definitely you hit the nail on the head. The window technology in Europe a decade or two ahead of window technology, even in the U.S. For a lot of import the windows from Germany and Austria or other places in Europe, and just not even just code windows. Just a code window in Germany now is a full triple pane window. That's basically a code window in Germany, and so it's yeah, the UPVC, yeah. Yeah, and I think the vinyl windows in the U.S. have they have stepped up their quality a little bit. I think a little bit, yeah. We'll have a slide on that, but in general, the U value on some of these newer passive house windows coming out of Europe are in the 0.11 to 0.13 range, and a code window there is in the 0.15 range generally there. Center glass on those is about R11, triple pane glass with the inch and 7/8 IGU. Oh, go ahead. Yeah, a typical Energy Star window is just a little over R3 or a 0.3, sometimes 0.28. You can get some triple pane windows in the U.S. that are in the 0.2 to 0.25 range pretty easily. So this is basically Scott and I made of kind of the building world as far as the health and quality and durability. And down here at the bottom, we have basically that'd be a building that set in class or a failing grade would be pretty much the typical building stock out there. And then a code building is not quite a C, but a D, D minus kind of range in terms of quality and performance. And then as we move up the scale, we have our C student here, which is Energy Star, LEED, which kind of C plus, C minus range. And then the DOE Zero Energy Home is a B student, and that's a standard put out by the Department of Energy, and their emphasis is doing a high-performance shell with the hope of being able to generate enough renewable energy on site to be net zero. And then here at the top, our A student is Passive House. And so that's kind of what we're talking about here is really that Passive House is the most stringent energy building standard in the world. And the standards in Germany, code in Germany looks a lot more like A and B than it does C, D, and F. And so that's kind of, we have a lot of catching up to do. We have a lot of opportunity to improve our buildings here in the U.S.
What is the
The passive house on the Hertz scale would generally fall anywhere from a 20 to a 40. It really just depends. The Hertz scale is kind of it's a scale it's all relative to a baseline house, and so the concept of the Hertz score is kind of silly in my opinion in a lot of ways, just because it's not like an EUI, for example, where you can't really directly compare two buildings because they don't have the same baseline, and so it's kind of hard to compare buildings with the Hertz score, and so it's just a whole different methodology. And so just to put things in perspective here, when we're thinking about code, it's not something we need to pat ourselves on the back for that we build a house to code. It's really the least safe, the least strong, least energy efficient building allowed by law. And so that's the D- building that we're talking about. And, code is not performance, it's not exemplary, it's not green, it's not. It's really the starting point of differentiation. So that's what all you folks are in the room here to differentiate and do something better than code on baseline. In terms of quality is not an add-on item. It's not a checklist. It's not a prescriptive pathway. It needs to be something that's designed and baked into the cake. It needs to be really part of the building, and the building physics need to be addressed. And so there's this little cartoon here where these guys just whipped out a machine, and now they're ready to slap a little go through their quality control checklist to make sure it's a good piece of equipment, that just doesn't work. So passive house is really, the cool thing about passive house is it's a purely performance-based criteria, and it's all about the energy use in the building, and you as a designer have the freedom to use your building science knowledge to make it work. So these are really the three.
It's not a prescriptive standard. It's really important. You basically have to meet. You're just going to talk about these metrics in a moment, but you kind of have an infinite variety of ways to do that. You have all the materials that are available to you as a designer or builder, or just what you want to use for different reasons. So it's you just have to put it together in the right way to get to these.
Yeah. So if you're one of the designers that has you're lucky enough to have a great solar gain, you can leverage that solar gain and optimize your design and actually reduce your insulation levels and optimize and balance everything. And if you have a project that's in the city or it's in a densely forested area, you can utilize better performing windows and super insulation to reach do how you want to do it. So the cool thing about passive house is this annual heat demand criteria. That's really what differentiates standards is. It puts a very strict limit on how much heating use can be used in the building over the year. It also has another limit where in the U.S. we talk a lot about energy and how much energy is being used per square foot in the building. That's a really common metric, especially in commercial buildings. Passive house takes that one step further, and they actually make you account for your source energy. And so not just the electricity they're using on site, but the energy that was required to produce that kilowatt of electricity. And then the other final tenet is the airtightness, which is a huge component of the quality and the comfort aspect and the durability. So just real quick, for those of you who aren't familiar with energy use intensity, you basically take all the energy use. If you took like your gas bill and your electric bill and you converted that all for the course of a year into BTUs and you divided that by your floor area, that gives you your energy use index, and that's per kilobTUs per square foot over the course of the year.
So this metric looks like it does not account for climate, is that right?
Oh, it's very climate dependent. It's extremely climate dependent. So anytime you do a project, you get, if it's not near an airport with a climate file, then you have to the Passive House Institute will generate custom climate set for that local climate.
Let me phrase the question as well. How much differently in northern Saskatchewan to meet that goal than you would in southern California?
Correct. Yeah. So instead of just upsizing your furnace and making your furnace bigger, if you built the house in Boise, it's a passive house certified in Boise, and then you moved it to McCall, where it's almost twice as severe of a climate, you'd need to have much thicker wall. It wouldn't meet the requirement. You're very right. It's very climate specific. And there's some modifications occurring to the standard. It has the Germans and the Passive House Institute in Germany and the Passive House Institute in the U.S. They have split, and the Passive House Institute in the U.S. is developing climate-specific standards that take that into consideration. Because if you're up in Alaska, you need a 24-inch thick wall to meet the standard. And so, but that's happening right now.
A little bit, so it made it a little bit easier in Alaska
and harder in Southern California. And just real quick, for those of you who aren't up to speed on the site energy versus primary energy, I just want to run through a quick exercise. If you're at a thermoelectric power plant, let's say you have 100, but basically 60% of that goes up to the stack as waste heat. Then about 40% of it goes out as electricity. We use a lot of that initial energy just as waste heat in the conversion to electricity. And so this is kind of going through how the Passive House Institute calculates the primary energy. Is we have, at the coal factory or the coal mine, we have the energy that goes in the extraction, the processing, the transport. At that point, if you start out with 100 units of energy, you end up with 90 that actually gets to the power plant. And then you have 60% conversion losses. And so you have 36 units of energy that go to the grid. And then at that point, the grid itself, you might have a few percent transmission loss there. And so in the end, the site energy, where you started out with 100 units of energy, the electricity is actually get to your home. So 3 units of source energy roughly equal 1 unit of site electricity. Compare that to natural gas. If you use natural gas to cook or gas to heat your hot water for your home, you have a much better source-to-site conversion. You actually lose very little distribution, very little in the extraction processing, and you get if you start out with 100 units of source energy, you get 90 units of site energy, and so that's more favorable in terms of primary or source energy. And that's why on the electricity side, even in a passive house which has a small heat, generally passive house that offset inefficiencies of the electrical system. And so with that in mind, the typical nomenclature in the U.S. is to use the EUI, especially on commercial buildings. With the passive house, if you have an all-electric project, to get to the passive house standard, you need to multiply that by the primary energy factor, which, again, that's another thing that's changing on the electrical grid makeup. And so essentially, if you have a house that is an all-electric passive house, basically your EUI is around 14. And so if those of you familiar with energy use index, that's a very, very low energy use index. And a lot of people confuse that, and they say, oh, my house is a passive house. It meets the 38.1 kilobTUs per square foot per year, but they're not doing the site-to-source conversion, so it's totally apples to oranges. So the cool thing about this standard is right away when you start a project, you have an idea of, with source energy, even if you just know you're going to build a 2,000 square foot house, is if you know you're going to be achieving the passive, it gives you a starting point at the onset of to get an idea of your carbon emissions and your on-site electricity usage. So it's a very good tool because you know really in the early phases how much energy the building is using if you design it to the standard. And so it's really great on net zero energy projects because these energy metrics to have a pretty good understanding of what your PV system size is going to be if you're trying to have either source or site energy net zero. You can quickly run through some calculations where you take the EUI and BTU and you can quickly see what your annual energy consumption is going to be. You can take PV system performance in Boise, convert that into what your system size is in kWs, and you have a really good idea of, hey, can I fit this system on my roof? Can I fit it in my lawn? Am I going to be, is net zero sense your project? If you don't have solar access and a building that's very dense and very tall, there's likely you're not going to have enough roof space for a PV system. So you can know really early in the project if I designed to this very stringent standard, what my PV size is going to be. And then the same kind of limit is set on the heating demand, and that's how much energy the house is predicted to need for the heating side of things. So again, it's just about early in the project, you can say, okay, if I designed the passive house standard, I'm going to roughly use this much annual heating demand just depending on the size of the home. Then another piece of the puzzle here is an optional part, and this is, again, very climate specific, but if you can meet the stringent peak heating load requirement of the passive house standard, you can also certify under that. And the kind of this originated with the concept of being able to heat the house with the heat recovery ventilator and heating that airstream and not having a traditional furnace. And so there's a standard that allows you, if you design the shell to a high enough level of performance that on the coldest design temperature of the year, if you can heat the house for under 3 BTUs, you can also meet the standard that way. And so if you design the standard and you have a 2,000 square foot house, you know what your peak heating load is going to be. And to put this in perspective, if you design in Boise a 2,000 square foot passive house, its peak heating load, if you design this criteria, is going to be just over 6,000 BTUs per hour. About human, depending on activity level, is 350 BTUs per hour. Family of 4 living in this 2,000 square foot house on a design day, one of the colder days, you can actually meet 22% of the home's heating demand, the peak load. That's how high these shells are. Yeah, passive house uses a little bit of a different design day, but essentially, instead of sizing your heating and cooling equipment to the absolute coldest temperature, like let's say it can get to -10 in Boise, we don't design to that. We design to a more realistic, like -2 or 10 degree type of temperature, and that's basically the temperature where if it's 10 degrees outside, if it's 70 degrees inside the buildings, how many BTUs do we need to add to the building? That 70 degree temperature when it's 10 degrees outside is lower performance. It has more heat loss. You need to input more energy in the load.
Are you going to have problems with like your because the set?
Yeah, we do. On the projects, we generally do a manual J as well. But we can, and all the equipment that's generally being used on these projects is all variable speed equipment. So even if the equipment is sized a little bit bigger with the manual, because the manual J calculations are a lot less precise and not as detailed as the passive house calculations. So if you oversize your equipment a little bit, you're still probably going to install the same unit, and it's going to have a range of capacity, and it can ramp up and ramp down to meet that load. And so it's generally not a huge issue.
I think the winter temperature is like 13, so you can design for lower than that.
Yeah. So yeah. And it's actually the passive house standard, I think, uses 20 or something for Boise. It might be 14. I do a lot of the projects I work on are in Seattle and Portland, and so and then McCall, and so I don't know the Boise design temps as well. But basically, what we're trying to achieve here is go from a typical building, which has, which is signified by this coffee pot here, where you have your glass coffee pot, you put it on the burner, and that's what keeps it warm as it loses heat. Moving towards the passive strategy, which is the thermos that just holds the heat in rather than having to constantly replace that for the lost heat with electricity. This is showing a picture of a project in Europe that before it was retrofitted, it looks a heck of a lot like this coffee pot, and then after the retrofit, it looks like a thermos. Very little heat loss. The blue is good. That means there's not heat escaping the building. Just a night and day difference in terms of control. And so one of the things that with a high performance, the free heat from internal gain inside of the building can be, and in most cases are, especially in North America with our higher plug loads, is as important as gains. And so passive house really isn't a passive solar standard entirely.
What happens in the summertime? The refrigerators, other appliances that are figuring out how does that
Yeah, it's I mean, similar. I mean, a regular house typically has all those things, except these appliances are even more efficient and generally have less heat output. But if they have a heat pump system that is used for the heating system, then that's usually used for a cooling system. So just like your refrigerator in your house, you want your refrigerator to seal tight and gasket tight and be really well insulated, and then the heat pump, pulls that heat basically out of the refrigerator and cools the temperature down. And the same concept works on a bigger scale. You have these plug loads generating heat in your home, and if you have multiple consecutive days in a row of heat, then a passive house is going to need cooling just like any other house would. And if there's not enough diurnal swings at night to do night flushing, or also the ventilation systems, they have a core bypass that does night flush and cooling, so it doesn't recover the heat inside the building. It actually rejects it and brings cool air in. And so there's a lot of strategies. And then one of the biggest strategies, of course, is the shading to prevent the solar gains from coming in, because those are really what can tip you over. When you have these low load buildings, you start adding a bunch of west facing solar gain, you can really spike up really fast. But even in regular poorly built homes, that's the same scenario.
Yeah, basically the gains that I could see there to some degree. So you have to do it. I think actually cooling mode will have to cool the house.
It's just you're going to be able to do it way more efficiently, because now you're not going to have a bunch of hot air infiltrating the house uncontrolled. You're going to be able to have control over everything and do it really efficiently. Go ahead.
Yeah, it doesn't feel like, so if you do cool it, you're going to get a lot more bang for your buck for the cooling.
Yeah. So although passive cooling is a big thing, but if you have a day where you have an inversion, it's smoky out, you want to batten up the hatches, you still have fresh air coming into the house that gets filtered first, and then your heat pump system. The projects I have in Portland that have cooling systems, we're talking like $12 in operating costs to keep the place cool. And so one of that Karuna project, that whole building, because the loads are so low, and it has exterior shading system, that's actually heated with a hydronic cooling system based off of the air to water heat pump. So it just slightly chills the floor, and that's more than enough to meet the cooling load, because the floors stay at a fairly moderate temperature. Then the latent load is dealt with a little dehumidification, but that almost never kicks on. Yeah, I mean, in Germany and Austria, that's the standard system is hydronic based for the most part, for heating. Yeah, there's generally, they don't, even in commercial buildings. Yeah, so I mean, some of the most comfortable passive houses I've been in are ones that do have hydronic based heating systems, but you think about it, in those systems we're using really low fluid temperatures, and so it's really, even if the heating system's not on and you're just circulating the water through the tubing throughout the building, if you have one part of the house that's getting solar gain, it's going to absorb that in that fluid, because if let's say the water that's circulating in the tubes, let's say it's just arbitrarily 68 degrees, if that room's 74, it's going to pick up energy. It's going to go to another side of the house that doesn't have any solar gain. Let's say it's 68, and it's going to even out the temperatures throughout the house. So it's a great way to do it, and you can create different zones, but it's an expensive way to do it. I think to go from a BTU to a watt hour, you divide by 3.41. 3.412? Yeah. Yeah, but joules, we don't work in joules. You're getting too little for us. Maybe the megajoules are. So this is a project that I modeled in the Passive House Planning Package, which is the software that we utilize to do all of our energy balance calculations in. And on the left here, this is a building that when it's built when it's dialed into the passive house levels of performance, it meets the energy criteria. But when we dial everything back, we keep the same building form, we keep the same windows as far as the sizes, but then dial their performance levels to code levels. This is kind of what you'd see on a typical code house, where you have your losses here from your walls, doors, roof, floor and slab system, ventilation and air leakage, and then those losses really dwarf benefits from solar gain and internal gains and active heating. So back in the 70s and early 80s, when people didn't have really high performance insulation systems and we had these high heat losses, the goal used to be to try to ramp up get as many solar gains as you can, because we're going to lose them all. And so that was where really the passive solar came from. But with the passive house, instead of having all this extra added heat, we're about the goal is to really minimize the loads. And so when you super insulate, use high performance windows and doors, make the building extremely airtight, that whole load, this is the same house just with higher performance components, you can get those heat losses down where now all of a sudden your internal gains and your solar gains are meaningful and they're actually useful. And so typical passive, we're generally reducing the heating demand by about 90%. Performance and optimization. And so, you know, word of caution is this was found out in the really early passive house projects where they were started to do the super insulation and the buildings weren't performing how they thought they would, and that was due to flaws in the building enclosure and insulation quality and thermal bridges and things like that. And so these thermal bridges, which used to get lost in the noise on a typical project that we used to get away on, these thermal bridges really add up to a big part of the energy component. And so, you know, the kind of the simple concept here is that heat transfer occurs from the warm side of the wall to the cold side of the wall. And if we have an R20 wall and we want to cut that heat flow in half to get to our really low passive house load, hey, all we have to do is double the insulation. We go from R20 to R40, half the we're on our way to getting a passive house. But it turns out it's not that easy. This is just a little quote from Dr. Feist, who's one of the founders of the passive house standard. He says, I was working as a physicist. When I was working as a physicist, I read that the construction industry had experimented with adding insulation to new buildings and that energy consumption had failed to reduce. This offended me. It was counter to the basic laws of physics. I knew that they must be doing something wrong. So I made it my mission to find out what and to establish what was needed to do it right. And so the early kind of experiments in low energy buildings really weren't panning out, and it just didn't make sense because technically the insulation, it's simple physics, it should work. And I'm going to kind of run through some scenarios here where let's say we have a standard 2x6 wall and, you know, typical cavity insulation, let's say, is roughly R20. And so a typical house is a 20 to 25% framing factor, and that's basically if you stacked up all the wood that was in the house to hold the structure up, it would account to, if you had a house with 4 walls, one of those walls would be entirely solid wood. So that's kind of the magnitude of wood framing that we have in a typical home. And so you can see the heat loss through this wall is really dominated by the wood instead of the insulation. So if we say, hey, I'm going to get some really expensive insulation and use, like, let's say closed cell spray foam in the cavity instead, and I'm going to keep my framing the same, you know, you cut your R20 heat flow in half, and that was going from the R20 to R40, but you didn't do anything about the R6. And so the heat loss is still the same here and here, and your overall wall R value only went from a 12.6 to a 16.5. And so we can't just look at our cavity insulation values. We need to look at everything as a whole. And so this concept is kind of the same as if you had a bucket that was leaking and you had 4 holes in your buckets and it's leaking water out. We don't address the actual leaks themselves, and we just made the bucket twice as thick. You know, we're not going to stop any of the water leaking out of our bucket. And so when we are designing the passive house, we're really focusing on the weak spots, which is the leaks and the holes in our bucket, rather than just making our walls arbitrarily R100 and then having a poor performing element right next to it. It's about the whole picture. And this is another example. If we started out with a R50 wall and we had to do an R50 cellulose wall, you'd need a wall that was about 12 inch thick, so you need like a 2x12 that was the structural portion of that. And wood's about R1.2 per inch, so a 2x12 is, let's just say it's roughly R15. That wall goes down from an R50 wall. Once you add the framing, it goes down to about an R32 wall, which is about 58% more heat loss than if you just called it an R50 wall. Here's an example. If we have that R50 wall, we had a 1 foot of stem wall exposed to the edge of that. There's enough heat loss through that, just 10% of the wall assembly being concrete. That heat loss to the concrete just dwarfs the heat loss to the R50 wall assembly, and the overall assembly as a whole is only an R7. And so you have to focus on these weak points in the building, and that's what passive house really focuses on, is these thermal bridges that add up to a lot of heat loss. Here's an example with steel. So if we have 99% of the surface area of your passive house as this R50 wall, and then you poke a 3-inch by 3-inch piece of steel just through one little part because your structural engineer, wanted you to do that. So this is the heat loss through the 99.9 square feet of cellulose here, right there. And just that little 3 by 3-inch piece of steel, 12-inch piece of steel that's 3 by 3 going through that wall, has more heat loss than the 99.9 square feet of the R50 wall, and that degrades the whole wall, just that small piece of steel, down to R21. So you have to be very careful, especially with structural steel, when you're designing these buildings. So that's 138% more heat loss. And if you didn't account for that in your energy modeling program, and you had that and continuous throughout a building, it add up to a large amount, and your building wouldn't perform how you expected it to. Could potentially have condensation and other problems as well. The same kind of philosophy goes with insulation systems, and the installation quality is very, very important with insulation. Very small flaws in the system can have huge impacts on the overall performance of the assembly, especially when you get into these super insulated assemblies. And also, air tightness is a very critical component. And basically, all insulation is, in general, is trapped air. That's why we used to be furry, was the hair trapped air around our body, and it kept us warmer. That's all we're trying to do with insulation. So you can think of this diagram here. We've got insulation with wind blowing through it. It's not effective. Just like if you go up to Bogus or Brundage Mountain and you don't have your windbreaker on and you start bombing down the mountain and you're just in a wool sweater, you're going to freeze because you don't have that air barrier. This is showing the level of degradation that a wall, this is what air permeable fiberglass is. Essentially, if with the 9-mile-an-hour wind, this R20 wall, if it's leaky and isn't airtight, it degrades all the way down to 7, which is 185. So, air flow has a huge impact on the overall performance of the building. That's why it's very important to control it. This is just showing how much moisture capacity warm air has over here versus cold air, which has implications in terms of durability. When we're talking about, we have outside air that's at 0 degrees, 80% relative humidity. The dew point's about -5, and that's the moisture capacity for that. And so if we bring that outside air on a cold winter day, bring it into our home and heat that 80% relative humidity air up, the moisture content of that air stays the same, but the storage capacity increases because of the additional energy inside. And so that's why homes in the winter, and especially in Boise and McCall, when we have these cold snaps, the humidity gets very low in the house because we have this uncontrolled infiltration that's dehumidifying and drying the home out. But going the opposite direction, if you have indoor air that's 30% relative humidity at 70 degrees, the dew point's 37 degrees, so if it is able to transfer through your wall assembly and go to the outside cold side of the wall through uncontrolled air leakage, you could potentially have condensation, moisture accumulation, and problems. So it's very important to build airtight. The amount of water that's transported through molecular vapor diffusion through a wall assembly is absolutely dwarfed by the amount of water vapor that can be transported into a wall assembly by air movement. It's kind of like so basically this whole, if you have a 4x8 sheet of drywall and that can diffuse paint on it over the course of a heating season through that whole 32 square feet of a 4x8 sheet of drywall is really pretty minimal, and it can generate. But if you have just a small leak and you have a pressure differential in the house, drive air through that hole, it can deposit just gallons of water. It's just, the same concept goes of a helium balloon. As you get this helium balloon, it's up next, and then it really kind of slowly shrinks down, shrinking molecular through the pores in that balloon of the balloon trying to equalize with its exterior environment. It's very simple. If you just pop a hole in that balloon, air will drain out of it right away. It's just much faster. How are we doing on time here? Ready for break? Okay. Yeah, that's fine.
Test.
Let's go through the stuff fast.
Okay, so a couple of things for those people that are either watching the recording or out there on the web. We put a new battery in this mic, so hopefully that helps. We may have been picking up most of Scott's vocals through Skylar's microphone. And also, we've been learning a lot about Passive House, which is definitely a next level in terms of keeping energy in the home or out of the home if it's cooling load season, versus our standard code-built buildings. So this is really interesting, and it's emerging in the United States. It was developed in Germany, but it's very interesting to see what we can do in terms of comfort and heating and cooling energy needs in a building when we really pay attention to the shell of the building and how we keep that energy in the building. So a really interesting topic. We've got a good group tonight, and thank you for all your questions, and we're going to get right back into it and the next hour of our program.
So real quick, the next kind of little section we're going to go through is going to be focused a little bit on just some of the fundamentals of comfort in a building. But it's important to know that humans we don't feel air temperature. We really feel heat loss from our body. And surface temperature control is critical to achieving thermal neutrality in a building, that point where you're sitting on your sofa and you really don't have a care in the world. You don't feel a draft. You don't feel any cold spots. That's really what we're trying to achieve in a passive house is complete thermal neutrality. And so a lot of people measure comfort in the United States, especially by a simple metric of air temperature. If it's wintertime and it's 70, 72 degrees in a room, heck, it's comfortable. But any of us that have actually lived in a building, especially in a cold climate like Boise, we know that surface temperatures have a major impact on our comfort, even if the air temperature is satisfied in the room. And so if we have a room that has 70-degree air, but we have a cold ceiling from a poorly insulated attic, or we have a cold floor from a poorly insulated or drafty floor system, or we have low-performance windows, we've all, I'm sure, on a cold day been next to a window, even though the room temperature is warm, we felt a chill coming off of that window. And that's because our body is constantly exchanging energy with our surroundings, and when you have a very cold object, we're going to radiate heat to that, and we're going to feel a sensation of coolness, even if the air temperature is warm. The same goes for walls. If you have ever sit next to a really cold wall next to your couch or something, you can really feel that energy getting sucked from your body and it's uncomfortable. Also, even if you have a really high-performance floor and you have a high-performance wall and you have a high-performance window and a high-performance ceiling, if when those components connect, if they're not connected properly or in a thermal bridge-free manner and there's weaknesses, you're going to have these radiating, basically cold radiators all around your home, making you uncomfortable. And then one of the biggest pieces of comfort in a passive house project comes from these really high-performance windows that we talked about a little bit earlier. And basically, in our climate zone, triple pane is a standard. And this isn't like a little 1-inch triple pane. For the most part, these are about 1 7/8 triple pane units with a really fat airspace filled with argon, 2 layers of low-E coatings. So the center of these windows perform at about R11, and we get an overall value in the R8 range when you account for the frame. So to give you an understanding of the importance of these windows, if you have an R50 wall, and I see this a lot on projects in Boise and McCall, where someone spends a lot of money, builds a double stud high-performance wall, and then they put an R3 window in that wall assembly. And I'm just concerned maybe people aren't doing energy calculations, because when you look at the building, that wall assembly as a whole, that window brings that, even with only a 15% glazing percentage, that window brings the whole performance of that wall from R50 down to R15, which is a 70% reduction. And so let's just say theoretically, you don't want to spend money on expensive windows. Heck, I'm just going to make my wall R100 because I don't want those fancy windows. That really only improves if you go from that R50 wall to an R2 wall or R100 wall, even though that's 85% of the surface area of that wall, really only gives you a 2% improvement. And so you really want to focus on the weak spots, just like the thermal bridges. And if you take that R50 wall, put in your R8 passive house window, your overall assembly value now is R37 compared to R15 with that R3 window. So it's a big, big advantage when we get into these high-performance buildings. And then, of course, these high-performance frames and the high-performance glazing systems result in no drafts and no local discomfort when you're near the windows. You don't have that radiative loss to the cold surface temperature of the glass. Moving on from the windows, just kind of back this whole idea of having control of your building. This is one example in typical construction where we absolutely just kind of ignore the fundamental physics of how buildings work. And most homes are equipped with a standard dryer, and when those dryers kick on, they basically exhaust between 150 200 CFM of air out of the building, and that air is replaced with air from the outside. And so when you run a dryer on a cycle for 60 minutes, you exhaust about 12,000 cubic feet of air, which in a 1,500, 1,800 square foot house, that's all the air in your home gets exhausted out and replaced with cold outside air that makes its way in through your garage, your crawl space, other flaws in the enclosure. And so in passive house, this isn't really the approach. We're not just ignoring these basic realities that if a CFM of exhaust air goes out of a home, then a CFM must come in to replace that. And then just to give you a little scale, we think of air as kind of this invisible light thing, but in reality it has mass, and that dryer running on its 60-minute cycle at 200 CFM exhausts 900 pounds of air out of your home. And so even though air is invisible, it's very important to think of that. That's just a lot of energy that's just getting wasted. In a passive house, we use units like these. I've got a couple of projects in McCall that have this unit slated to go in them. They're actually a heat pump dryer, similar to the condensing dryer. They're unvented, but they have a heat pump system in them that allows you to recycle that waste heat, and that instead of exhausting that energy, that heat actually stays inside the house and is a useful internal gain. Another thing to think of is in terms of it's the importance of air quality in a home, and I think we kind of fail to realize that our lungs have just a massive amount of surface area and a huge ability to absorb pollutants in our surroundings. Our lungs have about, if you spread out all the surface area of our lungs, about equal to half of a tennis court or the singles kind of player field, a lot of surface area. And we think of the, yeah. No, but that's the nice thing about the heat pump versus the traditional condensing units, where that heat would just build up in the laundry room generally, which was a nice pairing in that space potentially. Not that I completely recommend that, but that's exactly done that on a couple of projects. So that heat builds up normally with a condensing dryer, but with the heat pump dryer, it's actually recycling a lot of heat, so it's not building much because it's not constantly, as the condensation occurs, releasing more and more heat. It's actually reusing that heat and injecting it back into the drying cycle, so it doesn't overheat the space quite as much. But that's where you definitely would want a window for your laundry room in the summertime. But when you look at, with the mass of the house and everything, it really can get distributed out and not cause a huge spike in the whole house. It might just be a localized spike in the laundry room. Yeah, so I'm just going to cruise through some of this so Scott can get to his project. But just the really major importance of air quality. And, basically, the moral of the story is we live in a box, and because we live in these boxes, we need a ventilation system. We can't rely on chance and poor workmanship for fresh air, which is how most buildings rely. That's how most buildings get their fresh air, just accidental ventilation through holes and flaws in their building. And, indoor air can actually be far more polluted than outdoor air. And that's, I think, why a lot of people spend money on air freshener and things like that to try to cover the odors that are building up in their house. I'm just going to cruise through here because I want to get to some of Scott's stuff. Essentially, we need ventilation. We want to dilute the indoor pollutants in our house with fresh air, and do that with, this is just showing the unreliability of relying on natural ventilation for air, and versus what our demand for the ventilation actually is. Let's just skip through some of this stuff and get, do you think we should just skip straight to it at this point?
Air quality is important.
Yeah. And in most houses, we're getting it from like our crawl spaces. And so that's totally opposite of what the passive house approach is. Which can have radon. This was just kind of going through some of the fundamentals of the HRV. We can save it for another session. And now this should get us right to Scott. Looks like it's going to like shoot forward past your slide now. Here we go. Now Scott's going to talk about this great project that he's working on, this passive house in Boise.
Yeah, so that's the exciting thing. We're going to try to do one in Boise. So this one is scheduled to start. We have the homeowners here. We have the chemical engineer here. And Steve, Skylar, they're all having a hand in it too. So this is sort of a view of the entry. And this project is sort of in foothills east near Table Rock Road. And is it working? Great. Okay. So the goals were basically to take advantage of some really nice views that they had on the lot. They wanted an energy efficient home and a connection to the exterior and kind of a contemporary aesthetic, which without going too simple, I guess, too simplistic or minimalistic. There were definitely some constraints on the project. It's not an unlimited budget. There were some fairly strict neighborhood CC&Rs, and there's a wildland urban interface which really puts a lot of constraints on the materials that you can use that are fire resistant. It's a fire code. So this is the lot right here. So it also basically everything slopes downhill from there. So it's a nice sloped lot. The reason I put this up is just to kind of show that there's basically unobstructed solar access, which by chance is good for a passive house. It makes it that much easier to do it. These are the views. You have a nice view of Table Rock from below, and then sort of a little raised mound in the middle, and so that's basically looking south would be like this direction. This is just a quick tool that you can use to figure out how much shading there would be on that side. So this gives a reflection of basically the horizon line at that lot. So pretty good. Yeah, we don't have a lot there. You could imagine if there were a treed lot or a bunch of buildings, that you'd have a lot of sun being blocked. So the climate, just very quickly, we're in climate zone 5 in Boise, which you can see there's, it's comparable to New York and Boston. Chicago is probably a little bit colder, but we're kind of in that middle of the country band, not anything like northern Minnesota or, Jackson in that area. I just quickly wanted to point out the heating degree days is sort of a measure of how cold it is, how much time your house needs to be heated. In Boise, we're similar to Boston, less than Minneapolis. I put McCall and Stanley because they're places in Idaho that are cold. And Stanley has a lot. It's not as much as Fairbanks, but still it's a cold place. And you look here at Miami, they've got nothing. The opposite side, the cooling degree days, we're actually not as much as places like, I picked a couple hot places like Phoenix and Las Vegas, but if you compare it to, say, McCall, it's 3 times as much here in Boise. So heat cooling is an issue in Boise that we need to take into consideration. Just quickly in general for passive houses, passive house design, that the orientation of the building on the site is something to think about. It doesn't have to be perfect. You can have an urban lot, but you can imagine if you have it oriented this way that there's a lot of the sun will hit this south face a lot more of the time. You don't want to too much on the west or east because it's hard to block it from coming in. It could get too hot. But this would be maybe a not optimal orientation if you had the choice. So we ended up with something maybe that's not perfectly optimal, but just the way that the constraints were on the site. It's generally a cube. And this is our site plan with access from the
the street. There's a garage on one side, and then this is the footprint of the house. So we can go through this quickly, but I just wanted to point out that the surface area to volume ratio is an important consideration when you're actually going to implement a passive house design, a passive house standard. So if you have a big cube like this, you have a lot more interior volume to the amount of surface area. So you have a lot of heat, but not as much comparably places for it to transmit through. Same thing here, a single-story house is not as optimal as, say, a two-story house, and even if you go up to 3, it actually gets not quite as optimal. And this form factor basically showing that the more you change, you can have the same size house as far as the footprint, the square footage, but if you arrange it in a way that, like, this U, you have a lot more surface area where you can lose heat.
So notice all these have the same floor area, every single layout.
Yeah. And so this happens to be, this is the volume, essentially our thermal envelope of the project. And this ratio is at 0.93. I did it in metric to compare it to these graphs, which were here. So we ended up, this was a 0.11 for the middle and a 1.1 and 0.46. So we're somewhere in between these two. So I just wanted to point out that it's not a perfect box. You don't have to have a perfect box, but it does help to not have a very complicated form. So this is sort of an extreme example, but you can imagine the amount of surfaces that you could lose heat from on a design like this. It's possible to do it, but you have to consider how difficult it would be to detail that correctly. So this is the issue. So you have all these materials, we have all the components that go into a house, and how can you get all that stuff to come together to meet this 4.75 kilobTUs per hour per year? So we want to do that, meet those energy goals, make sure it's comfortable, and have good air quality, that it's durable, it's going to last a long time. So it takes a lot of, just general architectural design, that's part of it, but one tool that really makes it possible are these energy balance tools. So the Passive House Planning Package, this is the original software that the Passive House Institute in Germany developed. And that's what we're using on this project for now. There's another alternative. It's called Whoopie Passive. Basically does the same thing. It has some other advantages. But just to say that this is the tool that lets you optimize all those different parts.
And they were really developed for low energy buildings. Unlike a lot of the energy modeling tools out there, things like ResCheck are kind of more of a compliance tool that you'd use to be sure you're in compliance with something. These tools are really geared to optimizing low energy buildings and balancing things like solar gain and insulation and air tightness and high performance ventilation and mechanical systems.
Yeah. So this is the famous verification page. So it's an Excel-based, it's just a big, huge Excel spreadsheet. And what does it do? It's an energy modeling software, but what does that mean exactly? Basically, it's calculating the energy balance. So it's calculating all the losses that Skylar showed in those bar graphs and comparing those to the gains. And then there's a bunch of little details, but that's the general idea, is the energy balance software. They've developed this. The Germans did this in an Excel format, I think, because it's easy to see what's going on. You can put in an input, see what happens. Oh, it changes it by this much. I change these windows, it does this. And it's really easy to see. It's not easy to do it, but it's easy to see what's happening. They've done a lot of dynamic simulations that they've normalized. They've checked it against monitored data so that what their tool is doing is it's not perfect like you may be able to do a better dynamic simulation with different software, but it's the best way to do it
Yeah. Like it's the best thing about the planning package is that you can do just really fast optimizations of different design iterations, and you don't have to click a button and wait 30 minutes for a simulation to run out, and it's all real time. You get really good feedback. It's a really good tool for especially looking at the overall energy use of the building over the course of the year, and look at it more annually. It's great for that. And then if you want to look at more comfort-specific things, you can do a dynamic simulation and really look at different parts of the building.
Yeah. Do you have to do a solar analysis of the site and plug that in with software, or is it independent of solar gain? No, it is.
That's a component.
Yeah, it's a huge component. So I'll show you in 1 second. So that little, the reflective tool that I have a picture of, that's sort of just to get an idea of the shading of the site. But it's the climate data, which is, well, one more slide. I'll just go to it. Well, actually, I'll come back. So this is the climate data that would be generated that goes into that particular project file. And so basically it's taking the weather service data. They do some, I'm not exactly sure sort of process they put that weather data through, but it has to be in a certain format, and then you input it here. And you can't read it, but I think it's these columns are the radiation data for a certain site.
And it's monthly radiation averaged out.
So it's your solar data as well as your climate data.
Yeah, and so there's actually a tool in here. This is a graph I was going to include in. For example, you can size your solar thermal system and your PV system as well. There's a tool that lets you do it. Using your detailed monthly heat losses and gains. You can also look at something like, hey, if I install a solar thermal system and increase capacity, how much will it actually contribute to my heating load? And I think a lot of people would be surprised with how, even with a big solar thermal system, how little it actually contributes to the heating of even a low energy passive house. It's pretty amazing when you actually do the math.
Yeah, but basically this takes into account the temperatures, monthly temperatures. It takes into account your location, your radiation data, and I wish you could read it. But I just wanted to give you a sense of it. We don't need to really go through exactly. So these are those numbers that we were talking about before. So it's this one, and then you have the air tightness value, and basically the primary energy, I don't have it on here yet because I haven't completed that portion of this project yet. But this is where you know if it's working or not. And so in addition to the energy balance, this helps you determine the R values of your assemblies, so you can put all that information, what type of wall, what's my slab, what's my roof, and so it can help you calculate that. It helps you calculate your windows. It includes shading, so you can put in information about how your windows are shaded, how your whole building is shaded. It helps you with your ventilation design.
You can even do exterior shades and interior shades, and you can kind of see what impact those make in terms of overheating.
And it will calculate your internal heat gains, and it will also help you to determine, for your appliances, if you can, what level of energy efficiency you need for those appliances. So this is just to kind of show you the graphic of what the process is to fill out this spreadsheet. So it gets a little complicated, but it's really just these first yellow ones that are the most important, just to see how you're doing. If you're going, that's the heating side. Yeah.
You had mentioned earlier that I think the windows were European sourced. Are there a lot of the other components that have to be sourced from Europe, or are there supply chains and stuff here in the valley? And maybe you could give
Yes, so the question is about if the components that you need, specifically the windows, if they all need to come from Europe or it can be sourced locally. And I think that the two biggest things that end up being best to get from Europe right now are the ERV, the energy recovery ventilator, and the windows.
But those are the energy recovery ventilators. There's a couple of different ones I typically use on projects, and one of them, they have a warehouse of them in Denver, and then they have warehouse in Olympia and also on the East Coast, and so they're really readily available.
They're basically like a European product, but it's on the market here. It's no problem.
Yeah, and then there's really only one true passive house level European window. Like there's a handful in the United States, but one in Vancouver, BC. I'm using on a project actually in McCall right now, and those are passive house level windows that are coming in from Vancouver. But the lineals that they use to make the frame, they come over in a container from Germany, and then they're fabricated in Vancouver. but there's a few windows in Canada that can be used on a passive house. In McCall's climate, that would be really challenging, but you might be able to get away with some of the Canadian, like Cascadias or Lowens or something like that on a project in Boise.
You don't
Yeah.
anything specific.
So like the heat pump dryer that I showed in there, that's stocked in Boise. So the projects in McCall are just picking them up at Appliance Place. They brought in a bunch of them. And then you'll want to look at, your refrigerator and your dishwasher, just get the best ones.
Yeah, you just need to choose wisely for like your refrigerator or your dryer, washer and dryer, things like that. But other than the windows, everything is here. It's not, the prices for the windows are probably the thing that hopefully will come down and it'll make these projects a little bit easier. So this is just a sheet that you can see it's fairly simple, but this shows you how to calculate the R values. Just for example, for our slab, we have concrete and foam, can't really read it, but EPS, and we have an R value of about 26. So you can go through that for all your different assemblies, the walls, the roof.
So this gives you a really detailed heat loss. You're not just guessing like, oh, I have R40 insulation, my wall is an R20 or R30. You can really add in the structural components, and if you have some steel or some fasteners, you can actually, to a certain extent, account for those in here, and you have a really accurate picture of what your actual assembly performance is, which is really the gem of this software.
Yeah, and so right here, you say, oh, well, what happens if I try 6 inches of foam under my slab, or 8 inches? You change one number, and you can see that effect on the entire project.
Do you feel that crawl space is a better way to go, or slabs?
Well, it's slab. Yeah. I think that it depends. A crawl space can be done.
Yeah, if you do a crawl space, you need to think of a crawl space that's a basement. It's insulated foundation walls, insulated ground. Even a rat slab over that would be ideal, but it's not a vented crawl space generally. Okay.
Yeah.
But you got to insulate the slab. Definitely have to insulate the slab and the perimeter up around it. Uninsulated slab in our climate is a very silly thing to do.
Yeah.
Yeah, it could be. Yeah.
Yeah, you can do that. I guess the basement, almost.
Space is short basement. Yeah.
So this is a page where you put in all the areas of the envelope, so all the wall areas, the roof, the slab, so all those pieces of the house that can lose heat through that. And so you just let's see if I'll show you here. This is a calculation of the area of the house, so sort of the floor area, and that's an important number. So that's kind of the reference number that you have for that 4.75 number. And then all of the areas, this is a way that I do it with a little 3D model, and I can just click on the surface and get the area. And so I just label all these things, and it's easy to do it. You can change it. But you take, the west wall is this big, and then you go back and put it into that big sheet. So it's sort of an old method. There's the newer software makes this a little bit easier, and there is another way to get this to come into the spreadsheet quicker. But it's really not that many things once you get started. And then you have the Windows page. So you count all your windows and you label them all, and you input their sizes, and then you have to input where they are into each envelope piece. So I've got west wall, I've got these windows. So you can kind of see my groupings here, north, east, west. So you put in all the information about where they are, their sizes, and it's very detailed in the way that you can show how that window actually fits into the assembly. And the passive house, there are a lot of variables that you can look at. How good is my installation value? Did I over-insulate the frame, which something that doesn't exist in the U.S., but actually put insulation over the frame. So just to say that the level of detail that you can put with the windows is impressive.
Yeah, are you going to get to on the sizes too?
Yeah.
Okay.
You just mean as far, so
you can see the impact of like when you get a window that has an NFRC sticker on it, that's based on a standard window size. But with this software, if you change the size of the window and the ratio of the frame to the glass, you actually see how the actual window performance changes. Because if you have a really small window that's mainly frame and just a little piece of glass, that's going to perform a lot worse than a big window with less frame in relation to the glass, which performs higher than the frame.
Yeah, so when we get the information from the manufacturer, it's the glass has a U value and the frame has a U value. And it's just basically those two values.
And the spacer.
And the spacer has it.
And the install side value.
Yeah, well, that's what I was saying.
Yeah.
But those two values, you put that in, depending on the size of the window, after all the side value, the installation value, the spacers, at the end you get, it's maybe here, you get the actual installed U value of that window.
So you'll see on your project, your bigger windows might be R8, R9, and your smaller windows are only R5.
So shading, same thing. This is basically go through each individual case. Is there an overhang? Do we have blinds? Is there a tree blocking it? Is there a railing or something like that? So you can put in all those conditions. Ventilation. This is just a way to help determine the amount of airflow that you need in the house, and it depends on your air tightness plays into this. You put in the efficiency of your energy recovery heat or energy recovery ventilator, and this is a big impact on the energy. This I always see. You know, you can change the length of pipe from the unit to the outside. Like, oh, I'm going to insulate that with 1 inch of something, and it makes a huge, huge difference. So it's to that level that they're talking about. How are you insulating your ducts from your unit to get the outside air? So just quickly run through. This was the same energy balance that Skylar had. This was for this project. You can see that these are our this is our heating yeah. And then you have the internal.
So it's flipped upside down from mine. So yeah, we've got the solar gain here,
yeah,
internal gains, and then the active, which is supplied by the heating system.
So you can see that our gains are making up about half of the losses, and then we make up this much with our active heating system. So
this is by all means a passive solar house.
Yeah. What is your active heating system in this project? For this project, we're going to use the ductless heat pump, so the main splits. So just to reiterate those points, the continuous insulation, airtight, thermal bridge-free ventilation, and the windows. I just wanted to just refresh really quick and then kind of go through what we're going to do to meet those points. So the continuous insulation, this is a wall section. This is kind of our basic wall section. We're going to do a slab on grade, just a thickened slab with foam continually around the concrete. We'll do a traditional 2x6 wall that's going to be built with cellulose. And on the outside of that, there'll be it'll probably be a joist, a TJI, a joist, or one that we'll make on site, basically an 8 or 9 inch joist, or a sort of a, you can describe it.
Sometimes, yeah, you call them a Z joist. It's basically an I joist that you site fabricate with a strip of plywood and then 2x2s, and then you tack it all together, and it basically creates like a Larson truss on the outside of the house that just supports the insulation and the cladding system, and then you have a rain screen system after that.
I'm not sure everyone's familiar with the whole thermal bridging concept. So you can explain how that 2x6 doesn't make it to the outside of the building. Might be
yeah, well, so I should have. I wish I had a plan view of this wall, but basically, you can imagine the studs are lined up vertically, and so we're going to attach those TJIs right to the studs. So it will actually connect. There will be a thermal bridge that comes all the way through that wall. But we're just going to take that into consideration.
It's calculated for, and it's also wood and not steel. When you have, at that point, what do you have, like 15 inches of wood? And that is about 1.2 per inch, depending on the grain orientation and through the plywood. And we could say that that's, R18. I mean, it's not something that you really even see when you do thermography on the inside. You won't even really see the studs. And they're also slightly offset.
Yeah, and it's down to, I'm not sure that if we'll end up with 1/2 inch or 3/4 inch plywood. So that it's not a stud all the way out to the outside.
It's just like when you compare the heat loss through an eye joist or an engineered BCI or TJI, the heat loss through that versus a 2x12 rafter fraction, because you have this, small web of plywood or OSB in comparison to an 1.5 inch solid piece of wood. That's what the continuous insulation is in that exoskeleton that he's building.
Yeah, so the exoskeleton is just a way that we can use the least amount of material to create a cavity to fill it with insulation, and then we can hang our cladding onto it.
And the great thing about this cellulose wall is that it's going to be extremely low embodied energy. Really, if you look at the scale of insulation systems, this is going to be really close to like what you'd see in a straw bale house, especially in a straw bale house like in McCall, where they have a lot of snow loads and they end up putting a lot of steel in the building. This could probably best a straw bale house, depending on what kind of structural steel had to go into it as well. So it's a great wall assembly, and this is a really popular way of how they do it in Scandinavia and in Germany and Austria.
And so one more thing on this is that basically I wanted to keep this as simple as possible to build. So it's business as usual, as you would say, for the builder to do that 2x6 wall. It's easy to come back. You sheath it like normal. That's your structural sheathing, and you come back with those the I joists or the C joists and add those on after the fact. So let's see. This just shows that you have to keep that insulation continuous throughout the entire house. So in the attic, we'll have loose fill cellulose in the trusses. So thermal bridge free. We are going to isolate the concrete foundation with foam all the way around, and so this is I guess it's kind of considered a shallow frost protected slab. And this is just a piece of software called Therm that can model the heat transfer through that assembly. So you can see that we have, we want these warm inside temperatures to stay on the surfaces on the inside. So that's what we're trying to achieve by insulating this all the way around. So we don't lose anything to the ground or to this part of the foundation that might be exposed otherwise. Yeah.
You guys always do on-site building? Do any engineered building by someone manufactured and ready to the site?
No, not yet. But that's it's possible.
Some pretty good, well-built homes that are manufactured. But when I'm talking about it, a facility where they bring it to the site.
Yeah, it's possible.
And that's really big. And like in Germany and Austria, a lot of the passive houses that are built there are panelized homes. Where they do the panelized, they actually use the I joist as the wall stud. They build it up as a bunch of panels, and they slap it all together and finish it out. Structural foam right here.
So,
yeah.
So this fill here is structural, non-frost susceptible fill, so gravel basically.
Train rock. Yeah.
Train rock, yeah. And then we've got, basically we're making sort of a bathtub here out of foam to hold that. This is the concrete.
And it has more compressive strength than the soil that it's bearing on. So it's just a high density expanded or extruded polystyrene you can use. And all of the projects that we showed you earlier, even those multi-story projects, all have similar foundations to this, where you just engineer it out to the deformation of the foam, and it's just how you would engineer it out to the deformation of the local soil. So just do the math.
But we have to pass it through the city still, so we'll see what they say. It's completely, it's been engineered, it's normal. It's just a question of, showing the right information.
I don't know if you guys have driven down, I-80 in Salt Lake. That whole road system that's built up is built up on the same type of foam. And it's really common for bridges and roadways. They've been doing it in Japan and Europe for 40 years. So
the next principle is the air tightness. And so what we're using, a lot of planning goes in, I think, on these passive houses. I think the air tightness, the air sealing is one of the biggest issues that you have to face. How am I going to design this wall so that we can actually get it airtight in the field? And so this project is just going to use the structural sheathing And we may use normal OSB or like Goldie used, the zip sheathing. So that just what you have to put on anyway for your structural sheathing, we'll use that as the air barrier, and we'll tape that, or we'll use a fluid applied sealant one way or the other. And that continues all the way around. So I can show you here. The important thing is that air barrier is continuous. So how it meets underneath the slab, we'll have a vapor barrier under the slab, and that has to be connected to the OSB, and so it makes a complete enclosure.
If you go back one slide to how the structural wall cavity now, your plumbers, your electricians, they can run through this cavity. It's a totally, you can pierce all the holes you want through your gypsum and your drywall, and you have this uninterrupted air barrier that's protected in the middle of the wall. And structural engineers should really like this too, because your structural wall and your structural sheathing stays warm and dry, isn't exposed to the elements. It's going to be a much more durable wall.
Next. I think it's about 16 inches. And part of the house will be, we'll have siding, probably fiber cement board, and the lower half will have a stucco. But I think it's 15 inches that we have of actual thermal envelope. So it's thicker than obviously a typical wall, but it's not as extreme as you see in some cases.
With the higher R value, though. Yeah.
Yeah, I was just curious. I go back to that air barrier.
Yeah.
Yeah, that one. If you put the air barrier on the structural sheathing, are you doing anything or having any thoughts about really trying to isolate that insulation on the outside of the air barrier?
Yeah.
Yeah. So that's kind of the crux to this system, is what you do on the outside of the eye joist to keep that insulation in place and protect it, keep it wind tight.
It's called basically the wind tightness layer.
You don't want any air blowing into the insulation because it won't do its job if that's happening.
And instead, he's not using.
So
no, just one real air barrier.
One real air barrier, which is where this red line is, and on the outside here, which will basically.
It's also your drainage plane too.
Yeah, it's going to be the water-resistant barrier behind the rain screen, and we're going to use a membrane that just is it spun bonded.
Oh, if you use the Sega membrane, yeah, and these are big, tall membrane sheets, and you can easily tape the seams with also a vapor permeable tape, and you have a pretty generally airtight building. And he's not using like low density fiberglass bats or anything out there. That's also going to be high density cellulose, so it's going to be a lot less susceptible to any wind washing or anything like that. So even if it's not perfectly airtight, it's going to perform really, really well, even if it's 99% airtight.
So on top of that membrane, there'll be a rain screen, so another set of battens, and then there'll be the fiber cement board or the stucco system.
One question: what's the labor intensity compared to this, compared to doing foam blocks and foam panels on the situation you're talking about?
What type of foam blocks?
The foam blocks that can be all the way up to 12, 18 inches, 24 inches.
Oh,
we talked about that sound.
Yeah.
Foam panels, instead of the amount of labor that would take to do some of this stuff.
So just like big sheets of EPS?
No, he's saying if you did like a SIP home but with a SIP house, we'd have to do a 12-inch panel, and this is probably cheaper to do with a higher performance. Well, and then generally, unless it's a homeowner doing it himself, the labor doesn't. I mean, with an ICF wall, you can't. In most cases, you'd have to do an ICF that's extra thick, because the typical ICF is like our 18 or so. It's not a very high performance wall, and so you actually have to add. You have to get a thicker form additional insulation. In general, with this, even with labor and material, it's cheaper to do a higher performance, higher R value wall assembly than to do those assemblies. Yeah. I've worked on projects with those blocks, and when you do the math, it's more expensive to do that and use all that concrete at a much higher embodied energy as well than to do this higher performance system.
So it's 9 o'clock now. If people need to leave, you want to go 5 or 10 more minutes? We can finish. So the windows, we touched on those. We're going to most likely use a UPVC window from Europe. It's sort of the most cost-effective option that you can get from Europe. So unfortunately, no nice wood European windows. This is the ventilation unit that we'll most likely use. Basically, all these pipes go out to either a supply or a return. You have an equal amount of supply pipes as you do return, and so it's low flow. It's not a lot of CFM, but you tune that to what you need for your requirements.
And this just works in the background. If it's installed properly, you don't even notice it.
You don't hear it really, but you can bump it up for a bathroom, to exhaust out after a shower, or for your kitchen after cooking.
Smaller enough to.
They don't have to be. You don't have to use it, but
You wouldn't have to use this system, but this is the one that we will be using.
Who's actually going to build this house? Because you're talking about an extremely high performance home, and somebody who's going to need to have a lot of experience to make this actually happen.
Yeah, that's we're assembling a team as we speak. No, we're going to build it. Steve and I are the general contractors, and so we'll be putting together the team.
Okay. Yeah. So you guys build it yourself?
Some of it, yeah. What I think will happen is that, as I said, the framing, we want that to be, any framer can frame this house. There's nothing special about that. And I think that we'll step in on this first one, either work with the guys or, do some of the things like the I-joists, the taping of the seams. And I have installed this in a couple of houses in Salt Lake, this unit before. And so it's actually pretty easy to do these, we'll plan for these runs and things like that. So, there's a lot that's different, but my goal really is to make it not that different. And I don't think other than the insulation cavity, it's really not that different than a regular house.
It really isn't. And I've worked with a handful of builders in McCall that have done similar caliber types of projects, and the complex carpentry, like if you're a skilled carpenter, you can do this stuff. It's not a big deal.
Yeah, I built that wall with the gap on
Mm-hmm.
there's a couple spots that you can be careful about because how we get there, but
Yeah, I've done several projects with that assembly as well, and they've all gone very efficiently, even compared to projects where we did exterior foam and compared the labor with the I-joist versus doing sheets of exterior foam with long fasteners and the rain screen battens. And the I-joist system is pretty cool.
But the air barrier is all before that I-joist goes on. So we get that sealed, and then we'll add that on after the fact.
So will you do your first air barrier test after the D-joist?
Before.
Before.
Yeah.
So then you go and you'll nail all those on.
Yeah. There's not leakage through nails unless you miss.
Well, and that's the point of you got to have people that aren't.
Yeah.
Getting everything sealed.
No, it's true, and we'll have to we'll have to talk through the details. It's going to take some coordination and some learning, I think, to get the system right. Maybe we screw them on. We want to be more accurate. So
the projects I've worked on that have done that system where 0.6 is the limit for the passive house standard. I've probably tested at least 20 projects that are in the 0.3, 0.2 ACH range, and so it's totally achievable with a good plan.
So this is the south facade. We're planning some fixed shading over these south windows. This may seem a little bit back into the passive solar, a lot of glazing, but this is really more of a design choice because the views are to the south. So in addition to this fixed shading, which can only do so much, it works in a few months of the year in the summer. We will have some sort of possibly a roller fabric screen for these large openings, and then probably an exterior Venetian blind for some of the smaller openings on the west side and these two south windows here. But you have to consider the shading, especially with this much south facing glass. So the base cooling, this was heating and cooling. This is an example of the ductless mini split system. So you have this little outdoor unit, these two indoor cassettes. We'll have two of these, I think. It will depend on what Kara calculates, but it'll be probably similar to this. And then if there is, an extremely cold event where these can't work at their, say it's -20 for a week or something like that.
Polar vortex.
Yeah, you never know. It will install these little inexpensive baseboard heaters just to be used in the event of some sort of a really cold spell. Because these heat pumps can only work at their, their given rating to a certain temperature. And domestic hot water will have some sort of either a heat pump, a water heater, possibly a gas water heater. There is gas on this site, so we can take advantage of that. I think that may be it. So with that, we're 7 minutes over. Thank you to everyone. Are there any last questions?
Yeah, so if all things are equal in terms of comparing two houses, size, location the same, climate the same, what cost differential are you talking about between the difference of building, say, a HERS-rated home and a passive house?
It's a question that is really hard to answer.
Yeah, it's very difficult. I mean, especially it really depends on the baseline. I've worked on projects where it was actually cheaper to do passive house because the project starts out, the house is a expensive home with high-end finishes, and so the cost of the envelope is less of the total construction budget versus the interior finishes. And then there were projects that were going to be using PV systems and like things like ground source heat pump systems. We were able to scale those systems down dramatically, and passive house is actually cheaper. But when you're just trying to compare it to a production home, obviously, production home doesn't have a true ventilation system, don't really have a true air barrier system or continuous insulation systems. Typically, they're built over crawl spaces that are poorly detailed and poor moisture management. They don't have rain screening systems. I mean, there's a lot of upgrades. There's no doubt that you're going to see a price premium.
It'll be more expensive. And
You don't have a ballpark yet.
We don't.
For a custom-built home, on the custom-built projects I've worked on, you're looking at probably about 10% if you were already going to be doing like a wood window package already, like a Marvin window type of package. You were going to do hydronic type of heating in the house already. In those types of projects, the jump isn't really big. But when you're trying to go from like a production home all the way to that level of build quality, there's just a big...
Yeah, it depends where you start, and it depends kind of what your goals are with the project. I think if the clients really want very expensive finishes in a house, and maybe you can sacrifice finishes to get passive house things. I'm not saying that's what I would recommend, but you can play tricks like that where people say, "Oh, it was the same price."
Where they simplify the geometry
where they
too.
Simplify the geometry, so it's hard to say. I would like to report that back after we're done with this to you, though. Yeah.
What about cost? I'm really curious about the windows. Can you give any idea about the different, like, typical window package versus these windows you're talking about?
I've had projects that were Marvin specified windows, and we were able to import windows for less money from Europe.
Yeah, they're actually not as expensive as it sounds. The UPVC ones.
Yeah, but if you're going from like a builder grade vinyl window to a tilt and turn UPVC window that's going to last 100 years, one window is a scrawny little piece of junk that is going to last 20 years, and the other is a lifetime type of window with real tilt and turn roto hardware and gaskets and seals. And it's going to be a price difference. But I want to say even in the entry level UPVC, you're probably in the $40 to $50 a square foot range.
Yeah, just calculated that out. It's about $53 for a quote that we got.
Including freight too, right?
Including freight, which was like $4,000 or something like that. So
yeah, and so some of the higher end wood, aluminum. I've worked on projects where the square foot cost comes out to $110 a square foot for the glass for the window system, and then square footage of the windows of the window. But it's not going to compare to like a crappy slider window. It's just a way better window. Yeah, everything just went down 10%.
Yeah.
No. The reason
so much infrastructure and cost for something that is basically oversized. You don't need that much capacity, and so
You can definitely do it, and it's a great system, for sure.
It would really make sense if you could do sort of a little district system that would serve several homes.
The reason I asked because I know commercial is a good way to go.
It would be great for commercial. Any other last question? Thank you, everyone, for your attention.
Well, thank you everyone for coming. We've heard a lot about Passive House, which is an incredibly tight and efficient home envelope, and what it takes to achieve that. If you get it a little minute, please fill out your evaluation form so we can keep making these sessions better. And thank you all for coming. There's also, it's interesting to talk about the economics of this. There's some choices in the long run. If you're building a home, do you spend your money on finishes or an energy efficient envelope, which does pay dividends over the long run. So there are cost premiums to making a tight envelope, but it can pay off over the long run of a home. So thank you, Skylar, and thank you, Scott, for coming. And thank you all for being here. And hope to see you next month at the next session.